Everyone. So in this video here, we're actually going over max and min. So here's a quick refresher before we jump into it. There are two types of maximum or minimums or extremas in general. There is a local max and min, and there's an absolute. Okay. Instead of local, sometimes they might use the word relative. Instead of absolute, sometimes they might use global. So remember, absolute extremas could occur at the endpoints or somewhere in between. Local extremas only occur in between there. So just a quick refresher here. If you want to show whether there's a local max or min, you bust out a sign chart, which I'll show you in one of these problems. Okay. If you're trying to show that something is an absolute max or an absolute min, you have to make a table. Okay. Absolute extremas could occur at the endpoints A and B and any critical point in between. And then you're going to analyze the values over here. So that's it in a nutshell, okay? So the way that you can tell if they're asking for a local or an absolute is when they give you a closed bound. And I'll show you how to do that. And sometimes it's a little bit sneaky. But if they don't give you any type of bounds, know that they're implying that you're looking for something local. Okay, so let's take a look one more time here. So in 2002 here, part D, notice how we're looking for a maximum, but you got to ask yourself, is this a local or an absolute, right? If you take a look right here, this is a closed bound. So we're actually looking for an absolute maximum. Okay, how do we actually do that? I'm going to come back to it in a second, okay? In 2002 here, they're looking for a minimum, but notice how in the problem, there are no indications of any type of boundaries. So this right here would be a local. All right. What do you think this one would be for part D? Press play when you're ready, okay? Part D is asking for the least, so that's a minimum. And since there's a closed bound here, that's actually an absolute minimum. All right. Let's do a couple more. This one is an absolute minimum because there's a closed bound. And that is a closed bound, so that's an absolute. So that should be enough for you guys to kind of tell which one's which, okay? Now, how do we actually do them? I'll show you right now. Okay, so this one here is the absolute. You know, this one is probably the one that takes a little bit of time, but it's the one that offers a good amount of points, okay? So it pays you for your time if you think about it that way, okay? So here we go. So because we're looking for an absolute max, we know we want to create a table. You know what? Let me draw the table over here instead. And again, do this on a separate sheet, okay? So T is going to be for time. The absolute maximum could occur at the endpoints 9 or 23, and I'm going to leave some space for some critical numbers. We're trying to find the maximum of where the number of people in the park is a maximum, okay? So number of people in the park, okay? Now, this part should have been done in the previous parts of the problem, but let's talk about it now. If you want to talk about the number of people in the park, okay, do you have to consider the start, the in, and the out? Think about that there. If you want to know at a certain time how many people are in the park, what do you have to consider? Press play when you're ready, okay? So here, if you want to know the number of people in the park, you have to definitely consider how much you started out with. Okay? And you also have to consider how many people entered the park, but also how many people left the park. So we actually have to consider all three here. Okay? So the way you make this equation is you're going to consider the amount of people that started. So at 9 in the morning, notice how right here it says there are no people in the park. I don't care. I'm still going to put a 0 just to show that I remember. to find the amount of people that enter the park, we have to integrate e from 9, because that's when they open, to some time t in general. Okay? Because we're generalizing this equation. But we also have to subtract out the amount of people that are leaving the park from 9 to t, some time in general. Okay? Okay. Let me squeeze in an extra page here. I'm running out of space. Okay, so the amount of people in the park, I'm just going to call it A. Okay, so the amount of people in the park, I'll call it A equals all of this right here. So 0, all of that right there. Let me get rid of all the other stuff. Okay, so I'll call it A. To find the maximum, it could occur at the endpoints, which I have 9 and 23 here, or at the derivatives. So this is where you have to find a critical number. It's been a while since we've done that, but here we go. To find the derivative of a prime, the derivative of 0 is just 0. The derivative of just an integral is just the stuff on the inside. And the derivative of the second integral is just the stuff on the inside there. When you take the derivative of an integral, or if you take the integral of a derivative, they cancel out. And you're just left with the stuff on the inside. Okay? We take the derivative, we set it equal to 0 to find our critical numbers. Okay? So here, by now in this problem, you should have had y1 and y2 set up. Okay? So what you can do here is, for y3 on your calculator, you could call it y1 minus y2. Make sure that you bold it and that you uncheck the other two so that you don't graph y1 and y2. What we can do here is we can graph y3 and find our zeros. Really do pause here, okay? I'm taking my time with this problem. Obviously, in real time, you'd be doing it a lot faster, okay? So when you find your zeros, I'm going to cheat a little bit. These are going to be your critical numbers. So in part D for the first problem, it's 15.794 or 15.795. That's what you should have gotten, okay? So the zero should have been 15.794 or 795. I prefer to round it, so I'm going to use the 795 one, okay? Here's what you're going to do. 15.795, you're going to make a table, okay? So you could do this in many different ways. Make a table, okay? So maybe make y4 represent the integral from 9 to, on your calculator, you put x of y1 dx minus the integral of 9 to x of y2 dx. I'm just typing this out on our calculator, okay? And then here's what you can do. You can go to your home screen, so second mode. I know there's a lot of functions here, okay? But basically, here's what you're doing. You're trying to input all of these values as fast as possible. So make sure you understand the concept first before you move on, okay? So what I'm going to do here is I'm going to write alpha trace y4 parentheses 9. Do it again for y sub 4 of 15.795. And then I'll calculate one more time with 23. Okay? So, you know what? Let me do this just to model it. Actually, I don't have it saved here and I don't want to delay the video. But basically, you're looking for the largest number, and it turns out that it's actually right here in the middle. It's not always in the middle, okay? So according to the question, it says at what time does the maximum occur? So in this case, you would just say 15.795. Be very careful and listen to these words very carefully, okay? The scoring guidelines sometimes does not show the table, okay? For a variety of reasons, okay? Sometimes you can get away with not making the table if you have a really good understanding of your graph analysis. If you want it to be very robotic and pattern-like, make a table each time. So if you take a look here, they didn't really show a table, okay? It's not the case that if you find the derivative, you're just going to get the answer there, okay? You have to show that it happens. But anyways, they give you 2 points here. All right? Let me show you a couple more. Since we're on the scoring guidelines, let me show you where there's a table. Okay. So let me talk to you about this one here, just so that we have it in front of us. Part C, we're looking for an absolute minimum. Okay? So we make a table, which is right here. Absolute minimums can occur at the endpoints, so 0 and 18, or wherever the derivative is 0. So the amount of water in the tank, represents how much you start out with, 1200. So A equals 1200 plus the integral of W to get the water that's being pumped into it from 0 to T. And then we're going to subtract out the amount of water that's accumulated, that's being removed from 0 to T. So if we take the derivative there, notice how 1200 disappears. The integrals disappear, and you're left with W minus R. Okay? Notice how there's a pattern there, right? So here, we have to find out where W minus R is equal to 0. You guys can quickly graph this. Find your zeros. You'll find out that it's 6.495 and 12.975. Okay? We're going to take these four values and we're going to plug it into this equation here. And pretty much that's how they get these values. So if you look at the problem whole, it takes a lot of time, but you're earning a considerable amount of points. Okay? That's probably the most time-consuming part. I would definitely leave these for the end. I would do the other parts first, assuming that one doesn't depend on the other. Okay? But there you have it. The table, it's a very daunting task, right? It's very time-consuming, but you can earn a considerable amount of points. Let me show you one with a local extrema, just so you can get an idea of what I'm talking about. Let's do 2002 here. Okay, and I'll get rid of all this so that you're not confused and overwhelmed. All right, here's 2002B. They didn't give us a boundary, a closed interval, so we know we're finding a local extrema here, okay? So it says, for what value will the number of gallons of pollutant be at its minimum? First thing you want to do is, what represents the number of gallons of pollutant? Okay? So the number of gallons of pollutant represents P of T. Okay? To find the local extrema, you got to find its derivative. Conveniently, they gave us the derivative. So that's less work for us. Yay. Okay. So how do you find local extrema? Very straightforward. You set the derivative equal to 0. So right here, I'm actually going to do this with you guys because it's short enough for me to do. I'm going to go ahead and type this into my y1. And again, make sure that that negative 0.2 is a negative, not a minus sign, or else you're going to get some type of weird syntax error. I'm going to go ahead and hit graph. And And make sure that your window is on default, so zoom 6 if you want to go back to default. So based on the graph that I see right here, right now it looks a little bit like this on my screen, just to give you a comparison. I'm looking for a 0, and so far it's not crossing the x-axis. So what I'm going to do is I'm going to extend my x max. I'm probably going to change that to, let's go to 50. Okay, and it looks like when I go all the way to 50, it looks like it crosses. So looks a little bit more like that now. Okay, so I'm going to go ahead and calculate it. So second, trace 2 for 0. Left bound, I'm just going to put 5. Right bound, I'm going to put 49. And for the guess, I assume it's somewhere in between. So if you did it right, the critical number is 30.174. Okay, that is just a critical number. You have to prove that it's a minimum, so you do a sign chart. Okay, so you do t equals 30.174 right there. Local is definitely a lot simpler than absolute. It's quicker, but you do have to explain it, okay? So what you're going to do is you notice that if you just take a look at the graph, you notice that it's below the x-axis before 30.174, so you know it's going to come out negative there. And the derivative will come out positive after the 30.174. So here's how you properly write it. And there are many ways that you could write it here, but just be as explicit as possible. So it says, for what value of t will the number of gallons of pollutant be at its minimum? We're going to say at t equals 30.174, since p prime of t changes from negative to positive. That's it. We did a lot of that way back when. You guys did a Flipgrid video on that too. Okay? Don't say since it changes from negative to positive. Don't just say since it changes signs, because that's not specific, right? But there you have it. Hopefully that rings a bell at least. But if you need more of a refresher, reach out to me, okay? I guess we could do part C here since it's attached to it. So they're telling you, is the lake safe when the number of gallons of pollutant is at its minimum? Okay, so we know the time when it's at the minimum. So how do we figure out the amount of gallons, right? So here we go. P prime of t is the rate. So what we're going to have to do is we're going to have to consider integrating that. If we integrate P prime of t, we will get the amount of pollutant that goes into the lake. Okay? And we're going to go from 0 all the way up to the point where it's at its minimum. So in this case, it's 30.174. Okay? But we also have to consider how much we started out with. There were 50 gallons of pollutant at the beginning. Okay, and let's see if we have anything else. Okay, so this represents the amount of pollutant in the lake. In the lake at t equals 30.174. Okay, go ahead and compute that. Okay, so I'll go ahead and do this too. So you should be on your home screen. You're going to do 50 plus math 9 from 0 to 30.174 of alpha trace y1 dx. This comes out to 35.104. That's the amount of gallons in the lake at this time. So it tells you the lake is considered to be safe when it contains 40 gallons or less. Okay? 35 is definitely less than 40. Therefore, safe. Okay. Now, I wouldn't just write therefore safe, but therefore, you know the lake is safe at this time. Okay. So sometimes there are those follow-up questions there. Okay. Do your absolute best. I know these problems are lengthy, but you're looking for patterns here. Okay. And hopefully I did that for you guys, but keep going. Keep trying it out.